Okay, we continue with the discussion of Laplace transform. So what we are going to do, we will see the definition of the Laplace transform first, and then we will derive some Laplace transform pairs, and then we will discuss the properties, and finally we will apply Laplace transformation for the analysis of constant coefficient differential equations. So let's see. Now the definition. So I'm assuming that I have a function f of t, so a single variable function, and this is transformed, the idea of transformation, to another function which we call Laplace domain representation of this f of t function. So number one, this is small letters, meaning that this is time domain. Okay, one of the domains actually. And this one is capital letter, obviously, and this corresponds to what we call the Laplace domain. Okay. Sometimes we also use the word S domain to represent the, to mention this Laplace domain. Okay, so what do I mean by this small and capital F functions? Well, this is the definition. Capital F of S is equal to 0 minus to infinity, the result of an integral, as you see, e to the minus st dt. Okay, so this becomes the definition of, you may say, f of s. And f of s, this function, is called the Laplace transformation of this time domain, small letter f function. Of course, this variable doesn't have to be time, it can be anything, but then we should be thinking about the unit of s also. Okay, so if t is time, then this is time, t is time, t is time, t is time. As you see over here, I have e to the minus st. What should be the unit of s? That's the question. If we can understand the unit of s, now I get the idea for this s variables unit. Well, one observation. So this is about units right now. Okay. So if you have, for example, e to the x, if you have a function like this, e to the x, this would be x, let's say. This is something like 1 plus x over x squared over 2 factorial, x cubed over 3 factorial, and so on. So this is the exponential function, and this is power series representation. Details are not important, but the important thing is that, well, if x has the unit of seconds, let's say, okay, so a physically, let's say, measurable unit, let's say seconds, okay, then this becomes second square, this becomes second cube. So what are we observing? I shouldn't be adding, different units over here, isn't it? So clearly, I shouldn't be adding up oranges, apples, and oranges. They should all have the same unit. So clearly this is unitless. Then this tells me that if I have something like this, it's called the transcendental function again, then the units of this function, the variable which is the input of this function, let's say, the variable that is mapped by this function, x, it shouldn't have any unit, isn't it? So this should be unitless if it is in the exponent. Otherwise, I'm in trouble, as you see. Okay, so we have said that this is then t, over here is, let's say, has a unit of seconds. Then s, this should be 1 over second. Okay, 1 over second. Otherwise, I'm in trouble just because of this explanation. Okay, so 1 over second is, you can see this is the frequency variable. Frequency variable. And this is the reason that sometimes we call this s as complex frequency. Okay, complex valued frequency, but let's say it like complex frequency. So what do I mean by complex frequency? Over here, t is probably, at least in circuit theory, is a real variable. It's a real variable, but s over here, this s variable over here, it is, so this is complex field. S can be this variable can be a complex number. But at the end, for the sake of this calculation, we are considering that S has the unit of reciprocal of t. Okay? Whatever t is. If t is seconds, then it should be 1 over seconds and etc. So what we have seen. So this is a complex number. It can be j, it can be 1, it can be -5, etc. So I insert that complex number over here. Let's say that this is equal to 5. If it is equal to 5, I have this function time e to the minus 5t. E to the minus 5t is a decaying exponential. Then I multiply this function by a decaying exponential in this interval. It decays, okay, as t increases. Then I calculate the area under this. So if I change this s value to another value, let's say 6, then of course the area changes. So this is our variable s, which can be even a complex number. Okay. Well, there are issues when this integral converges, so on and so on, but let's think about them later on. So we have made this observation and about the units, and we are good to go right now. Now, how about the inverse relationship? Let's say that somebody tells me the f of s function, Laplace domain representation of this function. Now, what can I write about its time domain representation? So this is this. Okay. So this is forward Laplace transform, and this one is called inverse Laplace transform. Okay. It's called inverse Laplace transform. Well, what do I have? Well, this is what kind of an integral is this? Well, you see, this f of s function is again integrated, but the lower limit of this integral is, this is sigma. Okay, so sigma should be the element of what we call the region of convergence of f of s. There are some details. Maybe we should mention it, but maybe that's a topic of another course. So sigma is, right now, this part is the real part of a complex number. Okay, that sigma should be the region of convergence of f of s. So Laplace transformation is in detail studied in other courses. Okay, so for the circuit theory, we need this, basic information about the Laplace transformation. And this region of convergence is essentially discussed in 301. So what do I mean by region of convergence? Well, for some values of s, this integral may diverge. So what do I mean by this integral diverge? For example, let's say that f of t is equal to 1, and you are selecting s as minus 1. Then you have 1 times e to the t. You are calculating the area of e to the t function between 0 minus to infinity. So you get infinity because the area under this blowing up exponential is infinite. Okay. Now let's say that f of t is equal to 2. Again, s is equal to minus 1. Now you have 2 times e to the t. Then the area of that function is again infinite. Okay. So you see that in both cases, when s is equal to minus 1, for the constant function, this 1 or 2 function, I'm getting infinity. So what we see is the following. For some function, this integral diverges, and I'm losing the information about this function if this integral diverges. So this is the reason that this region of convergence is important. So what do I mean by that? Because I'm thinking that whenever I have an f of t function, I will be transforming it to another function, and it will be possible to go back and forth between those two functions. So this should be an invertible mapping. So if I know this, I calculate that. If I know this, I can calculate that by the inverse Laplace transformation also. Of course, the condition is this shouldn't be diverging. It shouldn't be infinity, because we have seen that two different functions, the function 1, I should say maybe ut or 2ut in this interval, unit step function, they are both resulting in the value of infinity when s is equal to minus 1. Okay? So clearly this becomes not invertible. So I'm looking for the values of s for which this integral is finite, it's not infinite. So that's called the convergent integral. So this is actually the same region of convergence of this function. So that tells us that for the values of s for which this function is not infinite, so meaning that this integral has converged, I can do this type of an integration, but there are details. Well, the details are s is a complex variable. That means that we are integrating over a complex plane. There are several other details, but for example this j, what is this j? This j is j squared is equal to -1. Okay, so this is the unit complex constant. There are several other details, but we don't need those details. We just need basic information for the meaning of this transform variable. Let's say it's units. So let's do not forget that this is just a complex number. As that complex number changes, this function changes, and so on. Okay, so for the inverse transformation, we will not use this inverse mapping, but we will be using some Laplace transform pairs, and we will recognize Laplace transform pairs and do the inversion. Well, that is good enough. Now, let's also think about one more time about the units. If this has the unit of, let's say, volts, maybe this is a voltage source, Vs of t. As time changes, the voltage value changes. Okay? So what is the unit of this one, f of s, left-hand side? Well, if f of t is, let's say, capacitor voltage, it can be a capacitor voltage, and I'm calculating, the area under this up to time t1. Function, VCT function, in between, well, you can start from 0 minus, but it doesn't matter because in between 0 minus and 0 plus, there is no impulse, so you'll get the same result. If you start from 0 minus or 0 plus, you will get the same result. So f of t is this function. Let's say that s is equal to 0, then I have 1 over here. So I'm calculating f0 right now from 0 minus up to, I should calculate the whole area, but let's say for the sake of simplicity, let's say that this function ends at t1, so it goes to 0. So what is the unit? If you calculate this, well, the unit is unit of f of s at s is equal to 0, okay, which is this area. Well, then this becomes the area unit. So this becomes the voltage, was this, voltage times seconds, because you can see that this part is in volts, this part is in seconds, then the area is, for example, if I take out a rectangle over here, this rectangle has the unit of seconds over here, volts over there, voltage times second. Okay? Let's go back. So this is voltage times second, because this is the area, and this was, actually you can see it from here. This is voltage, this is second, so I'm calculating voltage times second, and I'm adding them up, I get this. So this is voltage times second, this was 1 over second, so I get voltage in the product, in the, let's say, integrand. This is unitless as expected, it should be unitless. Voltage times second, this is 1 over second, ds. ds is just small amount of s, whatever it is, unit s. Okay? So if ds is 1 over second, then we have again voltage over here. So everything matches. Okay. Well, very good. So let's continue. One more note. This is called, maybe I should write it with this. This is unilateral Laplace transform. What do I mean by unilateral? Uni and lateral words. Uni means one, and this is side, isn't it? Lateral is, so this is a one-sided Laplace transform. So that means that this integral is only valid from 0 to infinity, because it starts from 0 minus to infinity. So there is also something else which we won't be using it, bilateral Laplace transform. So bilateral Laplace transform is exactly this one, f of s. But the only difference is that, as you see, this integral is starting from minus infinity and ending at plus infinity. So this is called the bilateral Laplace transform, double-sided, okay, or two-sided, okay, two-sided. So unilateral Laplace transform is our, transform of interest. The reason is that we will be applying this for the solution of circuits with some initial conditions, okay? Solution of dynamic circuits, systems with some initial conditions. So for this one, as you see, this integral is from minus infinity to infinity. You may consider that at the minus infinity, all initial conditions are equal to 0 from an engineering viewpoint. So essentially, there is no initial condition discussion over here. But bilateral Laplace transform is related to Fourier transform. For example, when S is replaced by j omega, okay, this becomes the Fourier transform, so on and so on. There are lots of discussions. But don't get confused if you see bilateral Laplace transform and unilateral transform, unilateral Laplace transform. They are different transforms, but of course they are closely related. Okay. Now let's erase this, and this bilateral Laplace transform is, again, one more time, topic of EE201. Okay, it's a third year, first semester course that you will be taking soon. Now, what should I do next? Now, I would like to derive some Laplace transform pairs. Let me write a little better. Pairs. So, let's start with u of t. And I'm looking for, let's say, its Laplace transform. So in this case, this becomes my f of t, and Laplace transform, I'm looking for f of s. Okay, how do I calculate the f of s function when this is u of t? Okay. So sometimes we use this notation, Laplace transform of u of t is equal to 0 minus to infinity. Okay, now f of t is u of t e to the minus st dt. Okay, now please remember ut is something like this. Okay, so it's 0 and 1. It's binary valued. At t is equal to 0, it can take any value, actually doesn't matter for us, but in some courses you will see that it's defined to take the value of 1/2. But for our course, you can leave it undefined if you wish. Okay, it's not very critical. So why it's not very critical? Because if I have this integral, 0 plus to infinity, okay, written like this. So I'm calculating from 0 minus to a point, let's say A. Then from this A, I go to the right towards infinity. And if I calculate this integral, not to an arbitrary A, but from 0 minus to 0 plus, okay, 0 minus to 0 plus. Now that integral will be equal to 0 because I'm essentially integrating over a point, okay. Again, if you are integrating the width of this triangle, that you approximate your integral in between 0 minus and 0 plus becomes 0. You will be getting a non-zero result for a 0 minus or 0 plus, essentially integrating over a point, only if you have an impulse over here, isn't it? But this is a standard, ordinary function. So if you integrate an ordinary function, whatever this is, in the integrand, okay, not an impulsive function, from 0 minus to 0 plus, you always get 0. So for an ordinary function, you can start this from 0 minus or 0 plus, doesn't matter. But for the sake of circuit analysis, we always start at 0 minus, but remember that this integral, the first one, 0 minus to 0 plus, is always equal to 0. So now I'm left with this, 0 plus to infinity. So in 0 plus to infinity case, this is always equal to 1. Okay. Now I should then integrate this one only. So what is this integration result? So this is e to the minus st divided by minus s, isn't it? So I'm only left with e to the minus st over here. And then I substitute t is equal to infinity and t is equal to 0 plus and I will get my result. Okay. So if I do that substitution, okay. So because of this minus, let's substitute this one first. So I get, instead of t, I'm writing 0, 1 over s, or let's do not confuse anyone. So I'm right now substituting e to the minus st divided by minus s, t is equal to infinity, minus e to the minus st divided by minus s, and substituting t is equal to 0. Okay. That is it. So this is this kind of substitution. Well, this one is rather easy. This term over here, when t is equal to 0, I have 1 on the numerator and minus s, this minus cancels, so this becomes 1 over s. That part is 1 over s. So how about this part? Well, this part is a little tricky. Why do I say a little tricky? When t is equal to infinity, I have e to the minus s infinity over here. Well, I have e to the minus s, let's write it like this, infinity. Okay. So let's focus on the special case of real numbers. So you can see that e to the minus s infinity is either 0 or infinity by itself. Okay. So, for example, s is a real number, let's say. S real. A subset of complex numbers is real numbers. So let's focus on the real numbers. So clearly you see that when s is a positive number and a negative number, as you see, we have different cases. When s is a negative number, for example, minus 5, I have e to the plus 5 infinity. Okay, it diverges. So this is the thing with, region of convergence. So you want this integral at the end to converge. Then you are selecting only the values for which this term is not equal to infinity, you may say. Well, it can be 0, non-zero, whatever the case is, but we don't want infinities. We don't want divergent result. So clearly, you see that for some values this diverges, for some other values it converges. And from this one, it has like binary value, either 0 or infinity. I'm focused on the values of s for which this term is equal to 0, essentially. Okay. So you can see that when t is equal to infinity is substituted, well, if s is a positive number, positive in this case, this term will be equal to 0. And then positive valued s values will be forming the region of convergence of this f of s, essentially. But there exists an s value, let's say, in the region of convergence. If this converges, then this will be equal to 0, because I have two possibilities, as you see. So what do we achieved? We have achieved the following. Good news, this is simply 1 over s. ut is Laplace transform to 1 over s. So what else? So first of all, why are we doing this? Well, in time domain, I have a function called unit step function. And in Laplace domain, I'll be calling the same function as 1 over s, okay, reciprocal of s function. You can say that, okay, handling this, constant function is easier than handling of this 1 over s. But it depends. It depends on your, let's say, viewpoint, etc. and etc. But this is an alternative representation of the same function. So you can always go back by the inverse Laplace transformation and get the original function in the time domain. So there is no loss of information. So this is like an alternative representation. One very simplistic way of thinking is, there is a mathematical object. This mathematical object is defined in time domain. Let's say time domain is like in Turkish. In Turkish you call this u of t. In some other language, let's say in German, the same mathematical object it's a different language. You call it something else. But it's the same mathematical object. And there's a translation between these two languages. And you will see that these two languages have some advantages when it comes to some operations. Maybe you will prefer this one or that one for some operation. So this gives you some, let's say, freedom in the choice of this language or the transform domain to do the operations. So we will be selecting one of these domains to do some, let's say, operations. Now, let's see. Our second example, f of t is equal to e to the alpha t ut, and what is the Laplace transform of f of s? Okay, so can we calculate this? Well, f of s is 0 minus to infinity integral e to the alpha t ut e to the minus st dt. I should, handle this integral. Again, maybe I should separate it from 0 minus to 0 plus, but, at the end, you will be, this is written as e to the minus s minus alpha t ut. Integrand is this. Okay. So, over here, the integrand is just e to the minus st. So, I have a bracket for over here, and the contents of this bracket is right now s minus alpha. So, it's almost like the same operation as you see. So, this is then s minus alpha, and I should be substituting t is equal to infinity, and t is equal to 0, 0 minus whatever you want over there. Okay, doesn't matter. Maybe I should write 0 plus just to be compatible with this. Okay, doesn't matter for our purposes. Okay, so this is the integrand, and then this is the antiderivative of this function. This is a definite integral, meaning that it has finite, specified limits. And then I do this kind of substitution. Again, the issue. So when t is equal to infinity, if I do this substitution, this is either infinity or 0. Okay. So for which values of s this would be equal to 0? Well, if this, again, this parenthesis, if this parenthesis is over here, is positive, if I put an infinity over here, this would be equal to 0. So this time you see that when s is greater than alpha, this integral will converge. Otherwise it will be diverging, okay, for s is greater than. But in this course, we are not worried about region of convergence. So there exists, assume, I'll be writing this, assume s is, let me say, as a real number, is sufficiently large so that f of s integral converges. Okay, so what's the meaning of this? Well, s is, let's say, 1 million, so it's like 1 million minus alpha. If you don't like it, make it 1 billion. If this is a positive number, okay, then substitution of infinity does not cause an infinity over here. So over here, then I should substitute this, minus, I have 1 minus s minus alpha. Okay, but as you see, each f of s has different region of convergences, and these are the details, but for our purposes, let's assume that this region of convergences, well, this integral is valid for very large s values like 1 million, 1 billion, etc. and etc. So no problems. I'm not even specifying, the s value over here. So, but I'm keeping in mind that this is not valid for all complex numbers, but only, the ones for which in the region of convergence. Okay. So this is good. Now we have found the following then. This f of s is equal to 1 over s minus alpha. Okay. Now, what else? Well, let me write this as a property. So there's a very simple property associated with this. If f of t is f of s e to the alpha t f of t, okay? But let me write ut just to, even though we don't need ut perhaps, but just to specify that this is like a one-sided operation. So this is a one-sided Laplace transform. This is f s minus alpha. Okay, this is a property. So actually, if f of t is equal to, this is just 1, then I have the Laplace transform of ut is 1 over s, f of t is equal to 1, e to the alpha t ut is, oh, I got confused. So I shouldn't be writing this because it's confusing with f, it's getting confused with this. So if f of t is ut, okay, now if I have this thing, then I have f of s, which is this. Instead of s, in the ut's Laplace transformation, I'm writing s minus alpha, and I'm getting my result. But this is not only valid for u of t, it is valid for any f of t, f of s pair, as you see. So assume that this is given to you. Okay. Now you are generating a new function, g of t. Generating means you are deriving, let's say, a relative of this function. What is the meaning of this? You are multiplying this function by an exponential. Okay. That's a new function. So this becomes the new function's Laplace transform, g of s. So you see that there is a relation in time domain between, let's say, these two functions. And there is a similar relation, there is a related relation, there is a connection at least, between these two functions' transform domain representation. Well, first of all, how can we show this? Well, proof is extremely easy. So let's do this. So let's try to calculate g of s. Okay. G of s is something like that. Now insert the definition of g of s. So this is f of t e to the minus e to the alpha t. Okay. Now this becomes then this. So I combined this exponential with this exponential and put it over there. And you see that now this bracket in the original Laplace transform definition, okay, was s. So if I call this bracket, for example, a strange s, something like a dollar symbol, then this would be f, that strange s. Because think about this strange s is again a complex number. So s is a complex number, s minus alpha is a complex number. Whatever that complex number is, I'm calling it like a dollar symbol kind of s. So this becomes f of, the Laplace transform evaluated at, this value, whatever that value is. Of course, this is a Laplace transform variable. This is equal to this, s minus alpha. Okay. So we see that g of t, when defined like that, has a connection with f of s, okay, through this. Now this is the idea. This is what we call shift. This function is, if s is real valued, it's shifted in Laplace domain. But this one is, as you see, multiplied by an exponential function. Two different operations in time domain and Laplace domain. One of them is just you shift the function to the right or to the left. Consider that this is like a real variable for now. And the other one is you are scaling this function with an exponential and so on. It's like multiplication of f of t. So you see that two different operations, but those two operations, are linked. Multiplication and this shift operation are, again, in a different language, they are defining, this object's transformation. This object is transformed to this object by this operation in time domain, and equivalently, that transformation in another language is described by this. Okay. So both of them are, this one is describing, let's say in German, this one is describing in Turkish the same object, and in Turkish there is a mapping, in German there is a mapping, but that mapping is a little different. Okay. Okay, so this is the property. Now, number 3. So f of t is equal to sine omega t ut. Okay. So if I have that, what is f of s? Okay. So how can I do this? Well, again, we can apply the definition, but you will see 0 minus to infinity sine omega t ut e to the minus st dt. Okay. So it's somewhat like a difficult integral, because I can do integration by parts, maybe I can evaluate this integral, but is there an easier way of integrating this? Okay. So the main idea is, right now we are using the following. Sine omega t is e to the j omega t minus e to the j is conjugate e to the j minus omega t divided by 2j. Okay. So what's going on? So maybe you can remember this from Euler's formula. This is cosine, let me call this theta. Theta plus j sine theta. Okay. So instead of theta, if you write minus theta, this becomes cosine minus theta, this one, plus j sine minus theta. Okay, that one. But since cosine is an even function, so this becomes either minus or plus, doesn't matter. Sine is an odd function, so I can make this plus, but I should make this minus then. Okay. So if I add those two, if I subtract those two, I get this part and this part cancels. And then I have 2j sine theta, and as you see, this 2j cancels that, and so on. Or, this is one way of looking at it. Let's erase. So you can write this as okay. So whatever I have over here, this is its conjugate, am I right? This is its complex conjugate. So there's a complex number. If I change t over here, please remember, essentially this is cosine omega t plus j sine omega t. Omega is 5, t is equal to 6. Then this becomes cosine 30 plus j sine 30. Okay? Or t is equal to square root of 2, whatever it is. So you get a complex number over here, and for this one, you get the complex conjugate of whatever complex number you have over there. So if this is a, complex number a, this becomes a conjugate. So if you are subtracting a from a conjugate, real parts are the same, and you are doubling the imaginary parts. So this cancels this, you get rid of j, so this becomes the imaginary part. So this is 2 times the imaginary part of, let's say, a. Okay. And divided, well, this is just this imaginary part of a. Okay. Because 2's are also cancelling and so on. So at the end, this is our basic result, this time for the sine function. Derived from Euler's relation. So what do I want? Why do I want this? Well, because I know if I call this, for example, alpha, then f of s is 0 minus to infinity, or let me write it like that. So this is the Laplace transform of sine omega t ut, but I can write this one as the Laplace transform of e to the j omega t minus j2 ut. Am I right? Because this is nothing but, this. Okay, so what else? Now, since this is a linear transformation, what is the meaning of this? Well, the meaning is this. This is my f of t. Okay, this is my f of t. So if I multiply my f of t by 2, then that 2 can go out of this integration. Okay? because integration scales by the argument of the integrand. If this is like f1 plus f2 in the integrand, then the result will be f1's integral plus f2's integral. So I can calculate these integrals for f1 and f2 separately and add them up. So I'll be, getting the sum integrated. So here is the issue then. Well, first of all, I can take this J2 out of this Laplace transformation. So if I do this, let's go over here. 1 over J2, Laplace transform of e to the j omega t ut, there's a bracket, minus Laplace transform of there is a bracket for the all. Okay, so I take this out, then this times that. Again, this is the scaling or homogeneity property for the linear operators, and this is the additivity property of the linear operators. Now, how about this? Well, this one. So this is e to the alpha t ut. So this is equal to 1 over s minus alpha. Okay. So I can recognize this as 1 over s minus j omega. Alpha is equal to j omega. So similarly, this is equal to the new alpha over here. Okay. So then this becomes 1 over s plus j omega. Okay. So one thing to remember, if you have e to the alpha t, this alpha value is making its Laplace transformation 1 over alpha s minus alpha. So the same alpha value is the singularity of this function. Okay. So if j omega is present over here as this alpha variable, then that j omega should be a singularity of this Laplace transformation. So this is j omega t minus j omega should be the singularity of this, which is indeed the case. So if I have that, okay, let's keep this. Let's one more line. 1 over j2, and I have 1 over s minus j omega, 1 over s plus j omega. I have this. Okay. Let's write better. Okay. So what is next? Now equate the denominators. So I can multiply by s plus j omega, s minus j omega. Okay. And then I'll be getting s square plus omega square. I have s plus j omega. Oh, there's a minus sign this time. Okay. S value cancels. I have 2j omega. So at the end, I'm getting this 2j cancels this 2j. I get a result like this, omega over s square plus omega square. Okay. I get this. So this becomes, again, there is a region of convergence, but I won't be mentioning the region of convergence for, every function. Like for this one, the result is this. For s values sufficiently large, okay? Sufficiently large s values, real valued s values, which are sufficiently large, I have this result as its Laplace transform. Okay, what else? Let me use this part. How about the cosine? So, let's do not spend so much time on cosine because it will be a minor observation. Laplace transform of cosine omega t. So how can I handle this? Now this is equal to the same idea this is equal to that. Okay. So previously for sine I was writing this difference. Now I am having a plus sign over here. So on the numerator, I'm calculating This is the conjugate of this one. So I'm getting the 2 times of the real part and dividing it by only by 2. So this becomes the real part of this e to the j omega t. Okay. So if I do that, let's follow it by our eye. So there's a plus sign over here. There's a plus sign over here. And instead of dividing by j2, I'm dividing by 1 over 2. So there's no j over here. There is no j over here. There's a plus sign over here. Okay. So if I have a plus sign at this point, so s plus j omega, s minus j omega. This time j omega terms cancel because there's a plus sign. I have 2s divided by s square plus omega square. There is a 2 over here. So we see that this is equal to s over s square plus omega square. Okay. The same reasoning. Okay. Okay. So that is good. Now, how about this? Well, this is 1, 2. Let's say that this is 4. This is 5. So f of t is equal to, let's say, t times e to the minus at. So what is this, f of s? Okay. So how can I handle this? But before the handling of it, maybe I should derive its property. So let me just to avoid some possible confusion, let me call this g of s. Property, if f of t is defined in transform domain, another transform domain by f of s. Now I have a function which is derived from this function by simple, multiplication of it, f times f of t. Okay. In time domain, I'm just multiplying by t. So the question is, what will happen to this? Okay. So if I call this my g of t function, okay, my g of t function after multiplication, so this would be the unknown function. It will be g of s, but of course I'm interested in what kind of mapping in s domain is corresponding to this multiplication in time. Okay. Again, these are mathematical objects. The same mathematical object is described in Turkish, in German. So mathematical object is the same object. It just modifies to another object called g. It's described in Turkish by this, the relation between modification of before and after modification. So the same object, how about it's in another language description? It becomes something else. But then how about this operation? How do you describe this operation in the other transform domain? Okay, that modification operation. Okay, so this is the understanding of transforms, representations, operators, etc. So, but let me simply try to calculate this. I need to calculate this, g of s. Okay. 0 minus to infinity, g of t, e to the minus st dt. Okay. So, well, I have something like that. But I know that g of t is t times e to the minus ft. So t times f of t, e to the minus st dt. Because, time domain definition of g is that. So what do I know? I know the following. I know that f of s, this is the thing that we know, is equal to 0 minus to infinity f of t e to the minus st dt. Okay. So there are of course more details to this. Now what is the connection between this f of s and this g of s? That is our goal, establishing that connection. Now there are some details, but let's say that I can take the derivative with respect to s. Let's say that I am focused on real numbers. So this becomes a function of a real variable. Okay. Then I can take its derivative. So d ds f of s. Okay. Now there is a derivative operator d ds over here. It jumps in. There are some conditions for that also, but you know, for our purposes, those conditions, let's assume that they are satisfied. So this is dds f of t e to the minus st dt. Okay. So there was a derivative operator over here, jumps inside of this integral, and so on. So I should take the derivative of this integrand essentially, isn't it? With respect to which variable? S, because I'm taking f of s's derivative. Okay. So you see there is only, you know, s present over here. So if I do this integration, I get, sorry, differentiation. So f of t is not affected. So f of t, and I have minus s, sorry, I got minus t. Let me write better. Let me move this. Minus t e to the minus st dt. Okay, because I'm taking derivative of essentially in the integrand, only s dependence is present over here. Derivative with respect to ss, you have this bracket. Okay, so this is equal to then 0 minus to infinity. Let me put this minus over here. F of t, t, or sorry, t times f of t e to the minus st dt. Okay. So what do I have? So I see, actually the thing that I want is, well, it is simply, I'm observing that this part is the thing that I'm trying to find, and it is related with the derivative of f of s. Okay. So you can see that this is minus dds f of s. Okay. So in order to get rid of this minus sign, I can multiply by minus 1 over here, and that gets rid of this. So minus derivative of f of s, it gives me on this t times f of t's Laplace transform. Okay. Well, this can be a little tricky at the beginning, because you see that there is a operation over here, multiplication by t. So this is minus d operator, if you wish. So this is like negative of differentiation with respect to, I mean, there is only one variable, but s. Okay. So you see that these two operators in time domain and in Laplace domain, they are linked. They are modifying this object's S domain description to the S domain description of this after this mapping by the same operator in time domain. Okay. So you see that, well, different domains over here represent these mathematical objects with different functions and also operators. So these are the corresponding operators, are also defined differently. So these two operators are corresponding to each other in time domain and in the Laplace domain. But at the end, what we have achieved is this. So how can I find this right now? Well, g of t, this. Let me write here, in order not to forget this, u of t. Okay. Now, if you call this f of t, okay, so this is f times f of t. So my final result will be, well, this is equal to minus dds f of s, isn't it? Because if you multiply t times this, so g of s is equal to minus dds f of s minus dds f of s. Okay. So I have that. So let's try to calculate that. So the Laplace transform of t e to the minus at uts minus dds of, well, let me say f of s again. So this is f of t, and f of s is 1 over s plus alpha. Okay. Again, this is its singularity at minus a, so this is minus a to the power minus a to the t, e to the minus a to the t, and I have, if you take the derivative of this, I get 1 over s plus a parentheses square. Okay, that is it. So how about this? Laplace transform of ramp t, ramp function. So let's remember what was ramp function. Ramp function was something like this. Okay, slope is 1. Well, when a is equal to 0, I get this ramp function over here, isn't it? So 1 over s square. I get that. When a is equal to 0 in this general result, okay, I get 1 over s square as the Laplace transform of this ramp function. Okay, so what else? Number 6. So the Laplace transform of impulse function. Okay, so what is the Laplace transform of impulse function? Well, impulse is always tricky in time domain, but you will see that it is rather easy to handle in Laplace domain. Okay, so what was impulse? Impulse is, we are assuming that there is a very tiny pulse. Tiny means that its width is tiny, but its height is, maybe it's very tall. Okay, so as its width is getting, let me have another color. Let me have this green color. As its width is getting tinier and tinier, its height is getting taller and taller, such that the area under this pulse is always equal to 1. Okay? And we show this. Of course, we don't talk about the height or, you know, the width, etc. At the limit case, I'm considering that, you know, there is a pulse with infinitesimal small, arbitrary small, let's say width, but arbitrary large height, and so on. So this is like an interpretation of it. The area under of it is 1. So this is the reason that we put brackets over here. These brackets are important because this is not the, you know, the amplitude or height of this function at t is equal to 0, etc. So this is in brackets. It's just denoting that area under this pulse, tiny pulse, is equal to 1. Okay. So the main properties of this, again, if I write this, I have something like that. So this function, it's in red right now, it's 0 everywhere except at t is equal to 0 we have that, you know, tiny pulse. Okay, so from 0 plus to infinity, now I'm, because of my this step assumption, this is equal to 0 because this function takes the value of 0. This part takes the value of 0, so integrand becomes 0. 0 times exactly 0, so 0 times something is equal to 0. So this is a simplistic interpretation, but good enough for our purposes. From 0 minus to 0 plus. So what's going on? So there is one multiplication property that is important. If you have f of t, or let me write more general, f of t minus delta t minus t naught, multiplying by, let's say, another, let's say, v of t, okay, then this is equal to v t naught delta t minus t naught. So this is the second important property. The first important property is this area property. Well, the second one is this. Second one is, if you have an impulse, again, let's say unit area at t naught, this is this, okay, and if you multiply this by a function, let's say that it's a continuous function, something like that. Now, what is the result? First of all, evaluate some t values. For t is equal to over here, so this is 0 because it's an impulse, and I have the value of function, whatever it is, but it's always 0. Okay? The product is always 0 over here. So similarly, select anywhere, the product is always equal to 0. So at the end, you see, always 0 except there is some activity at t is equal to t naught, isn't it? Because of this impulse definition. So number one, if you multiply a function and a Dirac delta function, impulse function, you get another impulse function. So what is the effect of this function? Well, again, let's remember our, this is like a story, but our story, there is a tiny pulse over here. So this tiny pulse is right now scaled by the value of this function at this point, isn't it? So the value of that function at that point is value v t naught. Okay? So this pulse, it is scaled by this v t naught, so it becomes maybe taller. Okay? And then, if this pulse is tinier and tinier and tinier, it's always scaled by the same number. So essentially, you are increasing the area under this pulse with this scaling. So you can see that increased area is due to this value of this function at that point, v t naught. But the important thing is, do not write the following. I mean, this is somewhat like a novice mistake, but some students, they sometimes think that if I multiply this, I get v of t naught. Of course, this is not the case, because v of t naught is the value of this function at this point, and it's not constant, obviously, because I'm multiplying an impulse by a function. The value of the function is just scaling this impulse by this value. Okay? So this is terribly wrong. Okay, don't do that. Let me even erase this. Okay? So why am I telling you this? Now I'm observing in the integrand an opportunity to use this knowledge. So what's that knowledge? When t is equal to 0, there is an impulse. Impulse is located at t is equal to 0. So what's the value of this function at t is equal to 0? The value of this function is 1. So I can write this part, the integrand, as, because of this property, delta t, e to the minus s0. Instead of t, I'm writing 0. So t naught in this explanation becomes 0. Okay? So this is equal to 1. So my integrand is simply delta t. Okay? Because this function takes the value of 1 at t is equal to 0. So at the end, what do I have? So I get this, 0 minus to 0 plus. I get this. And this is the defining area property of the impulse function. So again, I get a very simple result. It's just 1. Okay? Again, the exact details of this calculation is much more complicated. This is like, you may say, a story to remember the correct answer. But this is a good story. It's close to the reality. But it's not actually the truth. The impulse calculations, generalized functions, they are more complicated than this story tells you. But this is good enough. So we are right now not studying the generalized functions. They have their own theory, but we are trying to make use of these impulse functions, step functions, etc. and etc. Okay, so this is good enough for our purposes. Now, okay, this is 6. How about this 7? So this is the Laplace transform of delta t minus t naught. Okay? So this is our new question mark. So how can I calculate this? So again, I'll write a property. So if f of t corresponds to an f of s function in Laplace domain. Now, if it is shifted by some t0 units to the right, let's say, when t0 is positive, okay, it's like shifting to the right. Let me call this like g of t, shifted function. So shifted function has a Laplace transform. Okay. So how does this shifting operation affect its Laplace domain description of f of t? That is the issue. Now, how can I write this in terms of f of s? Okay. So again, let's try to write g of s 0 minus to infinity t minus t naught. This. Okay. So what is this? This is, as you see, g of t. This is g of t's Laplace transform. Well, I have this. Now, if you change the variables, okay, so I'm calling this t prime. So t is equal to t prime plus t naught. Okay, dt. And I'll be assuming that, you know, this t naught is over here. You know, t naught is a positive quantity. Okay, t naught is a positive quantity. So this will be then, well, let me see. T naught is equal to t minus t naught. Okay. Then, well, when t is equal to 0 minus, this integral is from minus t naught, okay, as you see, to infinity. So this is my t naught definition. When t is equal to 0 minus, the lower limit becomes minus t naught, and so on. So let's see. So if you do this e to the minus s, t naught minus t naught f of t prime dt prime. dt prime is equal to dt. So that is it. Now it's almost the end, but here is the case. So this is not starting from 0 minus, but it's starting from a negative value, as you see. When t naught is positive, this is starting from a negative value. But these functions, all of our functions are having ut. Okay? So f of t is defined as f of t is equal to 0 for t negative. Meaning that in our course, this f of t will be some function value, g of t times ut. There is a ut always like that. Okay? So, like, for example, over here, other examples, there is always ut because we are integrating essentially, we are interested in what happens after the initial condition. Okay? Our initial condition is, by our convention, that t is equal to 0 minus. So, before 0 minus, everything is considered to be equal to 0 from the engineering viewpoint for our course. So even though this is a negative quantity, you can move it to 0 minus, because from negative quantity to 0 minus integral is, well, doesn't matter, it will be equal to 0. So again, this would be equal to f of s with the integration dummy variable replaced by t prime instead of t in the conventional definition. So I get the following: e to the minus s t naught f of s. Again, these details of these calculations are topic of another course, but you know, they are as simple as this. I mean, it's quite a simple calculation. So how about this one? Laplace transform of delta t minus t naught. So what do we see? If I shift this function, f function, I get the same Laplace transform, but it's multiplied by e to the s, the amount of shift. Okay? So this is e to the minus s t naught times the Laplace transform of unshifted function. Okay? But this was equal to 1. So my result is e to the minus s times t naught. Okay? That is it. Very good. Now what else? Now we are approaching now important properties. Let's see. erase all of them. So this is, let me write a separate header for this, integration slash differentiation property. Differentiation property. Now, if f of t has the Laplace transform of f of s, now here's the issue. Derivative of f of t, d dt f of t, we will study this. This will be f times f of s minus f0 minus. Okay. So this is the derivative property, as you see. So if you know this, now derivative of that function has this kind of Laplace transformation. I will derive this. How about this? If I have 0 minus to t, f of tau, d tau, this is like a g of t function. Okay, this is the integration result. So this becomes f of s divided by s. Okay. So you can write this as d times f of t if you wish. And you can write this one as, if you wish, d inverse times f of t. Again, what is this d inverse? D inverse is simply the calculation of this area in between 0 minus and up to time t. As t increases towards infinity, you are calculating more and more and more area units. Okay? So as t changes, the area function changes, and so on. Okay, so how can I, handle this? Well, let's try to give proof. So derivative, differentiation property. So what do I have? So let me write it like this. So I have 0 minus, so this is the Laplace transform of f dot of t. Okay, so I'm focused on this. 0 minus to infinity, f dot of t, e to the minus t dt. Okay, so I would like to calculate this. So how can I calculate this? But maybe I should use this part for some integration by parts result. From AB, t is equal to BA. So this is called integration by parts. It's a calculus result. It is something actually very simple. What do I mean by something actually very simple? Everyone knows the following. Derivative of the product. You are taking derivative of the product. What is this one? Okay. Am I right? It is this. Now, if I integrate this from A to B, if I integrate it from A to B, and let's say that I need only this time, okay? Okay, let's move this one to the other side. If you move that one to the other side, you get this. Because this is the derivative and the integral, they cancel each other. Okay. So you are getting the this f of t times g of t, argument of the derivative operator, substituted by the limits of the integral, minus this thing, minus this term. It's the same as this term. So this is as simple as you see, product, law for differentiation. Now I would like to apply that because this is already almost like in that form as you see. So how can I apply this? I can write this like f of t, and then I integrate this one. No, that one remains as the same. I'm just checking it from here. From t is equal to 0 minus f of t. So I integrate this one. I should differentiate this one times d dt e to the minus st dt 0 minus to infinity. Okay. So g corresponds to this function as you see. So this is g's derivative and so on. Again, t is equal to infinity. Well, again, two possibilities for this term. Either this is infinite or 0, and we are selecting the 0 one by properly adjusting this s value. Okay. So this will be either infinity or 0 when t is equal to infinity, but don't worry about it. S is selected sufficiently large such that this product is equal to 0. Okay. This is, as you see, somewhat like tricky because I'm substituting also t is equal to infinity over here. But if s is sufficiently large positive number, okay, then this will be dominating this term, whatever it is, then this will be equal to 0. Let's assume that s is like 1 billion. Maybe that's not good enough, then assume 2 billion, so on and so on. So at the end, if I do this, I should be substituting t is equal to infinity, something, and I get 0. Then for t is equal to 0 minus, I get 0 minus, okay, or let me write this not to get confused. This would be equal to 0 minus f of 0 minus, and then how about this one? Now the derivative of this thing with respect to t is, well, minus s times e to the minus st. Okay. Then you have, take this minus s out, plus s 0 minus to infinity f of t e to the minus st dt. Okay. That is it. So this is what we have. F of s. So the final result becomes s times f of s, this term, minus f0 minus. But don't get confused. This one is capital F. This one is the initial condition in time. Okay, this is small f. So you see that the initial condition in time appears on the right hand side. It appears in, you may say, in time, 0 minus time, the value of this function at 0 minus, appears in this value, appears in the Laplace domain representation as it is. So we have such a result. So this is the property which we call the differentiation property, and it's a little interesting. Differentiation in time is like a process, but forget about this. So this is just simply multiplication by s. It corresponds to multiplication by s. This operation, this mapping, corresponds to a simple multiplication by s operation in Laplace domain. So this will be very important in the solution of differential equations. So for the integration property, well, instead of f dot of t, I'll be writing this g of t function, and again apply this integration by parts. And you will be getting this result immediately. Okay, it's the same thing. So what do I mean by that? So if I erase this part, and if I write integration, and if I write this like this gt, g is this, d inverse f of t, okay? So this becomes g, okay? Now, what do I need to change? Well, this is g. If I have this, so I would like to take, the derivative of this and integrate the other one. So if I take this, Let me think a little. So if I have that, I should be differentiating this. So I should be differentiating this. So this is my g of t function, okay? And I'm calling this right now my f dot of t function from here. So what is my f of t function? My f of t is e to the minus st divided by s, because if you take the derivative of this with respect to time, you get this function, okay? So apply this right now. Yeah, again the same thing. So f and derivative of this g function, let me write it like that, 0 minus to infinity. Okay, so what do I have? So again, when t is equal to infinity, this exponential, again binary valued, there is an s value for which this will be equal to 0, because otherwise it will be diverging. So I'm not worried about this case. So about at 0 minus, I have g0 minus e to the minus s0 minus divided by minus s. Okay? Okay, that is something. Minus, so this should be also minus, because this corresponds to this function. Okay? So I get, if you move this out, I get, let me use blue then, plus 1 over s, 0 minus to this, g prime of t e to the minus st dt. Okay. So what is g prime? So derivative of this integral, derivative of this function with respect to t, you get f of t back. Okay. So this part becomes f of s divided by s. Okay. Because you are taking the derivative of this function with respect to time. There can be details, but this is the result. How about this one? Well, g0 minus, this is equal to 1 over s, and there's a minus sign over here. But what is g0 minus? g0 minus is an integral from 0 minus to 0 minus. Okay. So essentially, this is always equal to 0. It's not even an integral from 0 minus to 0 plus. So this is equal to 0. So finally, we get our result, f of s divided by s. So this is the integration property. We verify this one also at this step. Now, why are these two properties important? These properties, you will see, they will be very handy when it comes to Laplace transforms. When it comes to, the solution of differential equations. So here's an example. So is this my example? Okay. So let's say that we have a differential equation in this form. Okay. So the question is, solve this differential equation such that you satisfy these two initial conditions and also t greater than 0 relation, the differential relation given. Okay? This is the differential equation solution problem. Now, question is, solve the differential equation using Laplace transform. Okay? So how can I solve this? Now, the main idea is the following. Derivative is, in time domain, an operation that we know. But in Laplace domain, that derivative operation corresponds to something very simple. Multiplication by s and subtraction by a constant value. Similar, integration is a process. But in Laplace domain, it's just this original function divided by s. So I'm assuming that I don't know this Vc of t right now. I have no idea. This is the question that I'm trying to find. But let's say that this Vc of t has a Laplace transform. Okay, I can go back and forth. I don't know this function yet, but if it has a Laplace transform like Vc of s, then d times Vc of t is, this is s times Vc of s minus the initial condition at 0 minus. Oh, that's already given to me. Minus v naught. Okay. How about second derivative? We haven't studied the second derivative, but how can I deal with this? Now, let me think about this. This is d of Vc dot of t. Isn't it? This is Vc dot of t. Okay. So I will apply the same thing then. Then this corresponds to s times Laplace transform of Vc dot of t, because here's my new function. Okay. So derivative function, if you wish, you can call this g. So this is s times g of s minus g0 minus Vc dot 0 minus, because I'm calculating the Laplace transform of, as you see, derivative of g of t right now. Okay. So derivative of g of t is s g of s minus g0 minus. So this is g0 minus. Okay. So how about this? Well, this is already given to me. So this is already over here. So this becomes at the end. So I need to multiply this thing by s. S square Vc of s, s times v naught minus this initial condition, v naught dot. Okay. So this becomes it. That is it. So at this point, we are all set. Again, let's look at the units. Are we doing something correct? So this is obviously volts, isn't it? Vc of t. How about this? We have discussed this. This is volts times seconds. Volts seconds, like meter square, okay? Or meter times seconds and so on, okay? So how about this one then? Oh, let's check at this one then. So this is volts seconds. This is 1 over second. We have studied this at the very beginning. So their product is volts. So volts minus volts. Very good. We are happy. That matches. How about this? This is volts seconds. So this is 1 over second square. So if you do this, this is voltage per second. Okay. Oh, how nice. This is also voltage per second, because this is the derivative of Vc of t at this time. Okay. Voltage per second. So similarly, voltage times 1 over second. So I'm adding up voltage per seconds also. So as you see, if you pay attention to the units, you can even write this by inspection, isn't it? Because there has to be an s over here. There shouldn't be anything over here, because eventually, if I differentiate twice, I know that I have to multiply by s 2 times, because differentiation in time domain corresponds to multiplication by s essentially. So s squared gives me, you see 1 over second square, and I get this result. Very good. Now, okay, I know those things, but how can I solve my differential equation? Now, we will be doing the following. I will take the Laplace transform of this equation. So what do I mean by taking the Laplace transform of that equation? D squared plus 3d plus 2 Vc of t is equal to f of t. But please remember that this is valid over this whole interval. Okay? This is even valid from 0 minus, but let's say from 0. Okay? Let's do not get into those details. T is equal to 0. So what do? If this is valid for t is greater than 0, can I multiply both sides by e to the minus st? It will be still valid. Okay. Now, if they are valid, for example, can I evaluate this equation in different times? So right-hand side, left-hand side, right-hand side, there is an equality. For t is equal to 5, I get a value. So derivative of this unknown function at 5 times 2, its rate of change times 3, its second derivative times 1, and so on. But at that time, when t is equal to 5. So it should be equal to this. So I have this equality for all times. So if you have this equality for all times, why not? At this point, let's put 0 minus. Sum them up. Okay. So this is what we mean when we say let's take the Laplace transform of both parts. You have an equality of left-hand side and right-hand side, then you do this kind of multiplication and you do the summation. Okay. So that is what we mean. So, okay, at the end, you have the second derivative Laplace transformation. Let me write this. S square Vc of s minus s times v naught dot. So this is corresponding to this first term. Okay. Plus 3 times s Vc of s minus v naught. So derivative of this is corresponding to this second term. Plus Vc of s times 2. Okay. I don't know that function, but its Laplace domain description is Vc of s. This is equal to Laplace transform of right-hand side f of s. Okay. That is it. Now, differential equation solving is, in time domain there is a process. In Laplace domain, now I have to find Vc of s from here. Vc of s. So how can I find Vc of s? So let's write Vc of s terms on the left and all other terms on the right. F of s, SV naught, plus V naught, plus, there's also, sorry, V naught dot, this is 3V naught. Okay. Okay, what is the Vc of s coefficient? It is s square plus 3s plus 2. Now this is equivalent to this. Now can I find Vc of s from here? Indeed I can. So this is, or let me write it like this, s plus 3 v naught dot plus f of s, this. So what did I do? I have divided both sides by this quantity, by this bracket. And I have combined, I have written that term over here, I have written the other term over there. That is it. Okay? So this is our answer. So this is final answer, but not in time domain, in Laplace domain. So this is the end of differential equation solution in Laplace domain, because we were looking for Vc of t, isn't it? Now Vc of t is found. So what do I mean by that? I know these quantities, and f of t, this is given in the differential equation. This is called the forcing term, right-hand side of the differential equation. For example, if this function is sine function, sine of t, now f of s becomes Laplace transform of sine, okay? So Laplace transform of sine t will be written over there, and that is the end. So we have found Vc of s, and then what else? We will be taking the inverse Laplace transform and finding Vc of t. So how about this and this term? So you see that this contains the effect of initial conditions, am I right? Only contains the effect of, maybe I should write only. Actually, this is what we call, maybe you will remember, VC zero input solution. we see, but in Laplace domain right now, we see 0 input. So input means f of t, external source, okay, or independent voltage source, current source, etc. If f of t is equal to 0, f of s is equal to 0, and then your solution is only this part. It contains the effect of these initial conditions only. Okay. Maybe just to remember, this is called the complete solution. This is the complete solution. So this is then the 0 input solution, this part. And how about this part? Only contains the effect of input, forcing term, let me write it like that. Or input. Okay. So we call this VCZS, zero state solution. That is, this is the general solution only when the initial conditions are equal to 0. Okay? This is the complete solution when the initial conditions are equal to 0. Contains only the effect of this forcing term. Okay, zero state. Now we are much more experienced. We know the meaning of state, state variables, and so on. So we see that we are ending up with this. Okay, zero state. So in Laplace domain, we are verifying that zero input, zero state decomposition is just a consequence of this operation. So we can maybe give a proof in Laplace domain by this trivial calculation. Now, let me focus on the time domain result. Okay, so let's find VC zero input t. So how can I find zero input? Input is 0, so in the general solution this term is absent, so I'm focused on this. So VC zero input in Laplace domain is s plus 3v naught plus this term divided by a squared plus 3s plus 2. Okay. So how can I take its inverse Laplace transform? That is the issue. Laplace inverse. So if I can calculate that, that will be the end of this exercise. I'll be getting zero input response. Again, this is capital letter in Laplace. This is small letter in time domain. So this, like with, curved V, I'm trying to indicate the small letters. So how can I do this? Well, first of all, I'll be writing this one as this. Okay. So if I recognize that this is like that, so can I write it like that? A, B. So this is called partial fraction expansion. Partial fraction expansion. So again, how can I do this partial fraction expansion? That becomes an issue. Okay. But let me do it this way over here. So if I have, like in our case, s plus 3 v naught plus another number divided by s plus 1, s plus 2, and I'm writing a over s plus 1, b over s plus 2. So these are a, b. They're just scalars right now. Okay, they are just scalars. So the issue is that how can I find those scalars? Well, in high school or in some other courses, you equate these numerators and the denominators. Okay, equate these denominators, sorry, and then you get two equations in A and B. Okay, so what do I mean by that? You write here s plus 2, you write here s plus 1. Okay, now you say that I multiply this by A, I multiply this by B, and then I will be getting, for example, the coefficient of s will be a plus b. on the numerator. And the coefficient of S is V naught. Then 2a plus b is the constant term, am I right? So on the numerator, after equating these denominators. So that 2a plus b should be the constant term of left-hand side numerator. Okay, so this is what you do in maybe in earlier courses or in high school and so on. This is like equation solving, trying to find a and b. We don't recommend this. This is not the right way to find a and b. So we should be using the residue method. So what is the residue method? It's actually a very nice procedure. So this procedure goes like this. I multiply, let's say, both sides. Assume that I have equality, s plus 1. Okay. If I multiply both sides by s plus 1, I put an s plus 1 then over here. S plus 1 over here. Okay. Then I still have the equality, isn't it? Because I multiply by the same, whatever s value is, by the same number. But there will be a cancellation like this. There will be a cancellation like this. There won't be a cancellation like that. So after you multiply by s plus 1 and these cancellations, substitute s is equal to minus 1. So previously I wasn't allowed to substitute s is equal to minus 1 because I get a 0 over here. Okay? But after the cancellation, this is just a number. How about this? There is nothing substitute over here, this is just a. This number is equal to a plus s is equal to minus 1, b times 0. Okay? So I'm finding a directly, as you see by this procedure. This is not my invention. This is an important method. It's called residue method. Okay. But the main idea is that you are finding a simply. You multiply this by s plus 1. You may cover it by your hand. And then you substitute s is equal to minus 1 over here. So you have minus 1 plus 3 v naught plus v naught. So after cancellation, you have minus 1 plus 2. So a is equal to 2 v naught plus v naught dot. Okay. So b is equal to, now what do we do? Now we multiply by s plus 2. Let's erase this. So I make this, multiply, I go back, I multiply by s plus 2. There's an s plus 2 over here. There's another s plus 2 over there. There's a cancellation. If you substitute minus 2 after the cancellation, this becomes 0 times a. A is absent. This term, whatever it is, I don't know the value of a maybe, but it's multiplied by 0. Okay? So b is present as it is. B is equal to, now I should be substituting s is equal to minus 2 over here. Okay? So 3 minus 2, I get 1. V naught plus v naught dot divided by, so this is cancelled because I multiplied by s plus 2. I'm trying to find b. Then instead of s I'm writing minus 2. I get this. Okay. So as you see, with the residue method, we are getting the results like that. So are they compatible with this equation solving? A plus b should be equal to v naught. Yes, they cancel. This is equal to 2a plus b. 4 minus this, I get 3. 2 minus that, I get this. So they are compatible. So we have solved this equation system without solving the equation system. Okay, that is the main idea. So you can say that why aren't we solving this equation system? The reason is the following. Assume that you have something like this. S plus 10. If you have something like that, so what are you going to do? I think you got my point. How many unknowns do we have right now? We have 5 unknowns because I have 5 poles, as 5, let's say, singularities of that function. Later on we will call them poles. Okay? So if I equate this, it's not a nice exercise anymore because I have, you know, For example, this product will be multiplying A. It's not very nice, don't you think so? But how do you find the value of, let's say, C? By the residue method. You find the value of C by inspection. Instead of S, you are writing -3, and this is -2 times, now this is -3, isn't it? -1 times, after this cancellation, I have this 1 times 2, so this is 7/4. This is the end, okay? So as you see, we are finding this coefficient without any equation solving because we were capable of, manipulating this equation such that we have only one unknown at the end left, and this is called the residue method. Okay. So of course, this shows the strength of this method. Instead of solving 5 by 5 equation system, even writing those equations are difficult because now I have fourth order polynomial multiplying A, another fourth order polynomial multiplying B, so on and so on. As you see, this residue method is the method to go. Okay. Now, very good. So if I have that, okay, so I have found this A and B values. Let's go back. So what is this? So this is A times e to the minus t ut inverse Laplace, B times e to the minus 2t ut. Again, the singularity of this appears, singularity of this function, s is equal to -2, appears as the exponent, as you see, like that. So A, this. B, this. Let me put minus then. And let me put everything, like with a different type of bracket, as a multiplier of u of t. So this is the end. As you see, the solution finding in Laplace domain, especially with the residue method and so on, it becomes very easy. So you don't have to do much other than manipulate these polynomial operations and so on. So this residue method was critical. Maybe this is a thing that you don't know very well. The other things you have already seen it in the differential equation course and so on. And for the partial fraction expansion, so this like expansion of this into many terms, summation of this, fraction expansion, it's very clear, I guess. So to do this partial fraction expansion, then we should focus on how we handle this residue method, etc. So I would like to recommend, just a note, check your textbook for the residue method examples. Okay, so that's all for now. So we will continue with more discussions later on.